Fred Howes was a great supporter of the CSGF Fellowship, and with this award, we recognize one or two alums of our program for their leadership, their technical achievements, and their character every year. This year, I'm very pleased to name Dr. Ariel Kellison as one of the 2025 Frederick Howes Scholars in Computational Science. Ariel completed her PhD in computer science in 2024 at Cornell University, began her career as a postdoctoral associate at Sandia National Laboratories, and recently accepted an applied scientist position with the AI company Code Metal. Ariel is an accomplished scholar, writer, and outstanding teacher, serving as a leader in the cross-disciplinary area of formal verification and programming language methods applied to numerical computing. Her early research focused on constructive analysis in Euclidean geometry and development of NuPerl, a logic-based proof development system. Though her PhD work saw initial success in stellarator optimization, she soon after changed trajectories to the new field of formally verified methods, combining her interests in formal methods, pure mathematics, computational methods, and physics applications. Ariel's current area of expertise lies in formal verification and type-based systems for error analysis, particularly in applying backward error analysis to formal methods. Her combined expertise and extraordinary capability in computational science and formal programming language has opened this new research area and then has driven it forward with groundbreaking results and powerful leadership. Because of her leadership in this field, she stands out as a rare student selected to be a member of the review committee for the highly selective Programming Language Design and Implementation 2025 conference. Throughout her career, Ariel has constructed and sustained an extensive network of cross-disciplinary collaborators across academic institutions, professional societies, and national laboratories, driving multifaceted research inquiries and contributing to the first TriLabs workshop on formal verification. Her organization of and ethical path forging for conferences, work groups, and large collaborations is celebrated by her colleagues, and her well-honed teaching prowess and mentorship practices span a variety of student experience levels. Dr. Ariel Kellison is a fearless mathematician, sophisticated scientist, and natural leader, inspiring those around her and serving as a powerful force in the development of the growing field of formally verified numerical methods. She exemplifies the technical prowess, scientific leadership, and shining character that Fred Howes encouraged in all young scientists. Let's recognize Ariel.
My talk today is about the problem of correctness in scientific computing and some formal methods that I developed during my PhD to address this problem. Computational science is undeniably incredible today, and it's not too hard to find examples. I'm sure many of you are working on these state-of-the-art problems. It's not too hard to find examples that are examples of this. So for example, ForecastNet, or Fourier Forecasting Neural Network, is a global data-driven high-resolution weather model that can predict both short and long-term weather patterns using state-of-the-art machine learning. So we've already heard from many people today about how machine learning and AI are changing the way that we do computational science, and this is an example of how things are changing. And one of the ways that we are now able to have incredible computational science today, one of the reasons we're able to, is because of these incredible advances in hardware. So for example, Fourier-Casnet's model only took 16 hours to train on 64 NVIDIA A100s, which at peak performance can compute 312 teraflops, floating point operations per second, if we're assuming 16-bit training. So if we do a little back of the envelope calculation, this is about 1,000 exaflops, or 1,000 billion floating point operations in total. All right, so we need a little bit of perspective. Okay, so as a fairly newly minted computational scientist or programming languages researcher, I don't have a memory of the Cray 1, which is the first supercomputer. But it's not that long ago, that's my point. First installed at Los Alamos Labs. I guess there was a little bit of competition between Lawrence Livermore and Los Alamos about this computer in 1976. Okay, and so peak performance for Cray 1 was 160 megaflops at the time. But That means that supposing, things like we had enough memory on the Cray 1 to actually train the Fourier forecasting neural net, it would take about over 200,000 years versus 16 hours for that training. 50 years ago, all right? Let's put that into more perspective. Okay, 2025, El Capitan now at Lawrence Livermore, so eventually they won the supercomputer, I guess. It's a billion times more performant and 1,000 times more efficient than the Cray 1 over 50 years. If we consider other machines that humans happen to care about, like cars, I'm not really a car person, but I luckily was able to find these online. So in 1975, this Lamborghini was the fastest car, 180 miles per hour, top speed, and efficiency, 10 miles per gallon, but who cares, it goes fast. All right, 50 years later, our fastest car is this Koenigsegg, okay, 310 miles per hour, not even twice as fast, and 13 miles per gallon efficiency, all right? That is, we're going back here, 1 billion times more performant and 1,000 times more efficient. This is an incredible advancement that we get to take advantage of as computational scientists. All right, but one of the great things about this, right? Here's a press release just from March 18th, 2025, so not that long ago. And let me read this. This is a press release from NVIDIA. These models, so ForecastNet, is already being used by weather technology companies, researchers, and government agencies to derive insights and mitigate risk from extreme weather events. It's already being used in government, right, to inform policy, making important policy decisions that affect our lives. That's what we hope for, right? As computational scientists, that's the kind of research that matters. It affects human lives. Let's port the code. So what happens when we port code? Is anyone holding their breath? I hope so. Some of you should be. All right, so we have some really nice research, recent paper, which looks at what happens when we when we compile code on different architectures. So here, the Fourier forecasting neural network was trained on NVIDIA GPUs, but El Capitan uses AMD GPUs. So what happens when we try and run code on these different types of platforms with different architecture? So this study showed that, okay, if we generate some random tests, we compile them for the different hardware, and then we compare the results, it turns out we get different results. And in fact, for floating point 32, so 32 bits or single precision tests, discrepancies were found in 9% of the programs that they tested. So 9% of the programs that they tested produced different results on different machines. So these discrepancies make it hard to know if our results are correct. And that's a little bit problematic if you think that we're using our results to inform policy decisions. So computational science is incredible today, but guaranteeing correctness is harder than ever. Why? Well, what is correctness? We first need a definition of correctness. It's very broad in computational science, not just in computer science, but I think it's particularly challenging in computational science to define correctness. So first we have numerical integrity. The example I just gave was that we want to avoid compiler-induced numerical discrepancies. We also want to minimize excessive numerical rounding, prevent floating point exceptions. We also have issues of concurrency and memory. We need to eliminate data races, avoid deadlocks, prevent memory faults. We have interface behaviors, very complex interfaces for our software and hardware. We need to make sure that these interfaces respect specifications at our system boundaries. And then we also have our domain-specific requirements. Okay, this is specific for your domain as a computational scientist. We want to make sure that we enforce physical or mathematical laws, for example, energy conservation, as much as possible. So why is guaranteeing correctness so hard today? Well, first of all, hardware is increasingly heterogeneous. We are often programming for a combination of CPUs, GPUs, NPUs, and FPGAs. Software is increasingly complex. Okay, this is kind of old. You know, the copyright is 2008 to 2022, but you can see here I skipped a lot of the lines, but it's about 200 lines simply for a sine function on AMD. This is AMD's library for an optimized sine function. Okay, so this is a basic component of what we need for computing, but it's very complex. How do we verify that it's correct? And also, our numerics are increasingly exotic. So not only do we have our traditional IEEE compliant floating point, single and double precision. We also now have tensor floats, brain floats, all of these different types of numerical representations. All right, so computational science is incredible today, but we have this statement, paraphrased, from the DOE NSF report from the 2023 workshop on correctness in scientific computing. If correctness is not proactively addressed, computational scientists and engineers risk producing flawed science and suffering productivity loss. So flawed science is about what you provide to the community. We want to provide the community correct results for good policy decisions. And suffering productivity loss is what you personally feel when you cannot debug your code, and it takes hours and hours to communicate the correctness of your code to your colleagues. All right, so how can we guarantee correctness? Well, we have a whole slew of methods available to us. Hopefully some of these methods you will learn about, as especially the new DOE CSGF fellows, in your coursework on computer science. We have code review and documentation here at the very top. So here I've listed these methods for guaranteeing correctness with increasing confidence in correctness. So starting at the top, we have the least amount of confidence in the correctness of our code. And then we also have increasing human effort. So code review and documentation means you sit down and visually inspect your code, maybe with a friend, to make sure that it's well documented and kind of does what you would expect it to. Then we have unit testing, continuous integration, fuzzing, property-based testing, concolic execution, type systems, abstract interpretation, model checking, symbolic execution, and proof assistance. Proof assistants are software tools that assist with the development of formal proofs by human-machine collaboration. This is very much a niche computer science topic, but we're trying to push it into computational science. And it's recently got a lot of attention from the mathematics community. So Fields medalist Terence Tao explains how proof checkers, so proof assistants, and AI can work together to prove the correctness of mathematical statements, but also prove the correctness of code. All right, so this first set of methods for guaranteeing correctness have a lot of good properties, such as low barrier to adoption. There are widely supported tools and familiar workflows that you can use today to ensure the correctness of the programs that you write. So for example, for Python, we have PyTest, which has support for unit testing, and the Hypothesis library, which has support for property-based testing, if you want to check those out. These methods are also incremental and iterative. They can be applied continuously during the development of your code. But they also have some issues. So for instance, limited coverage, you can't test all paths or inputs. A correctness guarantee means that your code is correct for all possible inputs that you send to it. Also, they're computationally intensive, especially in computational science, because they actually require executing the code. So if you have a very large code base, you have expensive time on a supercomputer, that means you have to execute your entire code in order to, for example, run all of your unit tests. Now, this second set of methods is what we traditionally call formal methods. So these are mathematically rigorous techniques for specifying, so that means saying what your program is supposed to do, how is it supposed to behave, as well as verifying software. Now, what are the benefits of these formal methods? Well, broad coverage is certainly one of them. Guarantees often apply to all possible inputs. That means, again, your program should behave as expected for all of the possible inputs that you send to it. That's a very, very strong guarantee. A test would say it would behave correctly for the specific input that you sent to that test. Formal methods usually say it behaves correctly for all possible inputs. Early detection. You can catch issues before you have to run the code. So it's kind of like a compiler front end. You don't have to run the code. It's like a compiler, very fast, hopefully. Okay, it doesn't actually have to run your code. But there are some issues. The first is a steeper learning curve. It requires upfront investment and expertise, right? These are mathematically rigorous techniques, so you have to learn about how to use them and what kind of guarantees they can provide. There also is the potential for false positives. That means that these techniques may report issues that aren't real bugs. Now, there's a sweet spot between these upper methods, which don't necessarily increase your confidence in correctness too much, but also doesn't require too much human effort, and these are called type systems. So why type systems? Well, several reasons. They're lightweight. Type checking and type inference can be fast and automated. They're scalable. That means they work on large code bases with low overhead. They're static, so they catch errors at compile time. Again, no need to run your code. And then you get a high confidence in correctness, so it rules out entire classes of bugs. Let's consider an example from C. All right, so here I've written a pretty bad program. My function foo tries to multiply what it thinks is an integer by a string literal, and there are a few other issues. So if I run my compiler, if I try and compile this code, it'll throw some errors. And what's happening is the compiler front end is actually type checking this code, and it produces these errors. So type systems help guarantee that operators are applied to the correct number of operands. That's the correct number and type of operand. So that's what's going on here. We're trying to pass a string literal into that operand. We get an error. User-defined functions are called with the correct number and type of arguments. So here we have an error because foo expects an argument of type int, and it doesn't get any kind of argument. And variables are supposed to be assigned to the values of the expected type. Here I'm saying that C is an integer, but then I assign it to a string literal. That's that error. So that's very useful. We know that there are some problems in our code, not by running it, but simply by checking with our compiler. That's what a type system can do. Now, rich type systems in other languages, so you might be familiar with C, but you might not be as familiar with languages like Haskell. So rich type systems can enforce stronger properties than the properties we just saw. So Haskell types can describe usage multiplicity in particular. And so this function, f, uses its argument exactly once. And that's what this %1 says. This one arrow is a linear function type, which specifies that this function uses its argument exactly once. And we can see in the definition of this function, indeed, it uses its argument x just one time, and simply in that sum. So for instance, if I try and write this function g, I specify its type, saying it should only use its argument once, and then I define it as x plus x. The compiler will, because of the type checker, say there's an error. You tried to use x twice in the definition of this function. You should only use it once, as specified by its type. So in my research, we designed type systems that enforce numerical accuracy and stability, so things that computational scientists are concerned about. So here is a program written in the numerical fuzz programming language, which computes the forward error of x divided by the sum of x plus y. So I call this function xdiv xy, because that's what it does. So this function takes two arguments, it sums them together, and then computes the division of x by that sum. All right, now when I run my type checker, it'll infer. That means it will tell you what the type of your program is, and also check that the types are correct. So in particular, it checks that any arguments that are passed to the function indeed have this type. So I'll run my type checker on this code, the code that we wrote, and it says that the type of this function is this. It's a function that takes two arguments. The first argument has this type annotation of 2. Second argument has this type annotation of 1. And then the return type has this interesting annotation, 4.4 times 10 to the minus 16. So we know that we take two arguments that are float 64s, and we return an argument of float 64, but there are some type annotations. What do these say? Well, these are actually guarantees in our language. The first is a guarantee of numerical integrity. So this programming language actually tracks the round-off error that's produced by this function. So in particular, it says that this function produces at most 4.44 times 10 to the minus 16 relative rounding error in double precision. That's what this annotation on our return type tells us. It also enforces mathematical properties, so domain-specific requirements. It says that the real valued function that this program implements is actually Lipschitz continuous in each argument, with Lipschitz constant 2 in the first argument, that's what this annotation says, and Lipschitz constant 1 in the second argument, that's what that annotation says. So that's pretty cool. Now, we can go from these local guarantees about a function to system scale correctness guarantees. How do we do that? Well, with function composition. When functions compose, local guarantees become global. So if I were to define this function g, and it has a type annotation of 3 here on its argument, and it says that it returns a value that has this rounding error bound, and if I were to compose as xdiv xy with g, it will tell me the total, the return type will be the total rounding error that is produced by the composition of those two functions. So this enables modular reasoning for large systems. Large systems inherit guarantees from their parts. So each of our individual functions are guaranteed to have some type that tells us the information about the rounding error and its Lipschitz continuity. And then we can, as we compose these functions to produce larger programs, larger code bases, get full guarantees about our total system. So in summary, computational science is incredible today, but guaranteeing correctness is harder than ever. Type systems provide lightweight, scalable enforcement of correctness guarantees and the types of problems that we're worried about. They statically rule out common bugs and can enforce domain-specific guarantees like round-off error bounds, stability guarantees for numerical stability, and Lipschitz continuity. Of course, I did not perform any of this research in isolation. I have my amazing mentors from Cornell and Princeton to thank. David Bindle was my advisor, Andrew Appel from Princeton was my co-advisor, and Justin Su is a fantastic mentor on programming languages. I'm very thankful to the DOE CSGF for the autonomy that I was able to get during my PhD to be able to perform extremely interdisciplinary research. So not just working with my advisor, who's a numerical analyst, but also being able to work with programming language experts and formal methods experts. I don't think I would have been able to do research that's so incredibly interdisciplinary without the CSGF. I also did my practicum at Sandia National Labs and was able to meet some really fantastic people there who are pushing formal methods research, so Sam Pollard and Heidi Thornquist, who are pushing formal methods in computational science. From that, we also spanned into excellent collaborations with people at the University of Michigan and Lawrence Livermore National Labs, and I have some really fantastic undergraduate and graduate students that I was able to mentor and continue working with on correctness problems in scientific computing at Cornell. So again, in summary, computational in science is incredible today, but guaranteeing correctness is harder than ever. If you want to check out some of the languages and type systems we defined, you can look at Athena types on GitHub, and you can also check out some papers that we wrote from QR codes. So thank you.